Warm welcome, everybody. Good to have you here. Get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you out of nowhere. And today we have a problem from the 2005 AP Calculus BC exam. This is BC exclusive. We're covering a BC concept with polar graphs, doing calculus with polar curves. So if you're an AB, sorry, but this video is not for you. If you'd like to observe, feel free, but it's possible that some of this won't make any sense. So I'll see you in a year or so. Okay, if you're stuck around and you're ready to solve this, give yourself about 12, maybe 15 minutes. I see that it's 4 parts, so I haven't looked at this problem before. I feel like I have seen it at some point in the past, just because I recognize this kind of funky shape, but who knows when I saw that in the past. Definitely wasn't 2005. I was not doing calculus in 2005. 20 years ago. I have been doing calc for a while, but not 20 years a while. Okay, I gotta imagine this is a calculator problem just because the curve is not really that nice. It's theta plus sine 2 theta, but try to do as much as you can without a calculator. If you absolutely need a calculator at the end, go ahead and use it. And then come on back when you've given it a shot and see how we do it here. All right, let's get started. So we have the curve. It says it's above, but it's not really above. It's kind of to the side. Maybe in the actual AP exam it was above. The curve above is drawn in the xy plane and is described by this equation. Now, this is not the usual polar curve format, so it doesn't map out a familiar curve. And that's only from 0 to pi, so it's only defined from 0 to pi, which kind of makes sense. We see that the angle sort of goes like from 0, and then at pi it has something out here. So, yeah, this would be kind of a cool beanbag sort of couch situation going on. You know, maybe they have this kind of thing like in Denmark or Sweden or something. Okay, so of course r is measured in meters. They give us some units, interesting. And theta is measured in radians. The derivative of r with respect to theta is dr d theta, and they already took the derivative for you. It would have been pretty easy to do it, but they took it for you, so you don't have to take it yourself. It's kind of cool. And let's get started. Part A says find the area bounded by the curve and the x-axis. So literally like the area of all of this. And if we were going in terms of theta, we would be filling it in like this, wouldn't we? So the amount of area that we're adding is according to how far the distance is. So when r is very far, that's adding a lot of area. When r is very close, we're not really adding that much area. Okay, it seems to get like pretty close right here, and then it starts like getting further away again. So those are some interesting locations, the furthest point and the closest point. Or at least I think it's the closest. Kind of looks like it's the closest point, other than 0, of course. So it gets far away, and it seems like it reaches its furthest away, then it sort of curls back. So yeah, I would say that that's the furthest spot. And this seems to be the closest spot after that furthest spot. So there might be some kind of maximum minimum thing going on. Okay, but anyways, we're finding the area. So we can be confident that the area goes from 0 to pi, that this whole region goes from 0 to pi, just to make sure r of 0, that's just 0 plus sine of 0, so 0. And then if we took r pi, that's going to be pi plus sine of 2 pi, which is just 0. So it makes sense that the r value is pi. All right, so yeah, I can be confident now that this entire space is covered from theta equals 0 to theta equals pi. So let's use the formula for the area. And so we have 1/2 integral from 0 to pi of r squared d theta. So this is going to be 1/2 0 to pi of theta plus, oh, interesting, theta plus sine of 2 theta squared. Now, this could be done by hand. I don't think they're going to have you do it by hand, but you could do it by hand. This is going to end up being theta squared plus 2 sine of 2 theta. Oh, sorry, plus 2 theta sine of 2 theta. Okay, yeah, this is already going to get a little bit complicated. Plus sine squared of 2 theta, which we're going to have to change using the double angle formula for cosine. So this would turn into 1/2 minus, oh, and this is sine squared of 2 theta. So this would turn into cosine of 4 theta over 2 plus 2 theta sine of 2 theta. So yeah, this probably isn't going to be, I mean, you could do this by hand. It's not like it's not doable by hand. I would probably have done it by hand on the AP exam, but it certainly doesn't, it's not a short problem if you do it by hand. And we have 4 parts to go on here. So I think it's safe to say that we could use some kind of calculator for that. So you could just use a calculator for it, all the way back here. You don't need to write as far as I did. But if you were doing it by hand to get all the points, you would want to use some of these things and then evaluate at some point. But we'd have to use the power rule, and then we'd have to do a little bit of integration by parts here because we have 2 theta times sine of 2 theta. So yeah, that gets a little bit complicated. Let's just plug this into an integral. So I'm not recording this on the screen necessarily, but I am just using Desmos, which is what you would have access to. So the integral from 0 to pi of the expression, I might as well just use x plus sine of 2x. Don't forget the dx, and we're also multiplying by 1/2. I'm getting 2.4674. I'll just show you guys. Might as well just show you. Put a quick little screenshot on there. So this would be our value, and it would be in like square meters, I guess, since r is measured in meters. I don't think they really mentioned that being important with the units or anything, but oh well. Okay, part B. Let's move on since we've established we need a calculator here. Find the angle theta that corresponds to the point on the curve with x-coordinate -2. Okay, so if x equals -2, got it. Remember that x is equal to r times cosine of theta, which means that the x-coordinate is defined by theta plus sine of 2 theta, but then all of this is times cosine theta, which is certainly, not a particularly nice function. We would say -2 equals theta cos theta plus cos theta sine 2 theta. Yeah, not particularly nice. We're looking from 0 to pi, by the way. That's our domain. And the reason why I mentioned that is because we're going to have to sort of look at this on a graph. So how would I do this? The way that I would prefer to do this is to look at when their difference is 0. So in other words, I'm going to graph this. And we're going to see if I add 2 on the other side. When is this equal to 0? That's the question. What angle? And when I graph it on Desmos, just to let you know, I encourage you to do the same, you can just use x, because we're just finding values that satisfy an equation. We're not focused too much on a graph in particular. So I'll show a screenshot of that too, because I can do this fairly quickly. We're going to graph x cosine x plus cosine x sine of 2x, and then plus 2. And we get this kind of crazy looking graph. I encourage you to check this out if you haven't already graphed it when you were trying to do this problem. That's what the graph looks like. Pretty crazy. So see what I did on Desmos is I literally just typed in the expression and I found where it equals 0. So that's our value. So theta is equal to 2.786. This is in radians, of course. That's the angle where the x-coordinate is exactly -2. And it seems to be reasonable, right? Because this is like not quite pi. Where is this sitting around? This is sitting around 5 pi over 6. I mean, it's not exactly 5 pi over 6, but it's like around there. And that's kind of where this x-coordinate is -2, you'll notice, sort of at the angle, like 5 pi over 6. It may not exactly be there, but it's somewhere around 5 pi over 6 that we get an x-coordinate of -2. So this seems to be consistent across the board, yeah. And we're definitely using Desmos in a calculator now. Sorry I didn't share the screen with Desmos, but at least I'm able to take screenshots and just post them for you. Okay, let's look at part C. Oh, part C is nice. It's more conceptual, actually. So we had to find the angle. We had to find the area in part A, the angle in part B. But here it's just saying that the derivative is negative. And what does this say about R? What does this say about the curve? Well, dr d theta is how the radius is changing as theta gets bigger. So that means that as we increase the angle from pi over 3 to 2 pi over 3, let's look at where that's at. Well, I think those are at our special points here. Yeah, I think that's like literally right there. So if we look at the angle pi over 3, which I had to guess, I have to guess it's right there, to 2 pi over 3, which I'm guessing is right here, dr d theta is negative. So what it means is as we go from, 0 degrees to pi degrees, as we're passing through sort of this direction, the radius is changing, right? The distance is changing. We have a very far distance here, but then as the angle increases, our distance decreases. Now it's like this short. And then as it keeps going forward in angle, the distance keeps getting shorter and shorter. It makes a little weird little bubble there. Do you see that? So that's literally what dr d theta means. What this says about R, it says that as theta increases, the distance from the origin decreases because the dr d theta is negative. That tells us that as theta increases, dr d theta is decreasing. What does this fact say about the curve? That's a good question. I think that is kind of what it says about the curve. I mean, it curls in, I guess you can say something about the shape. The shape of the curve curls inward towards the origin from angle pi over 3 to 2 pi over 3. That's the best that I think I can answer that. I might not get full points for that. There could be something very important that I'm missing here, but I think it should be all right. Yeah, I don't know what that says about R necessarily. I mean, it says, got it. Yeah, it just says R is decreasing. Got it. Yeah, and what it says about the curve is more about like the shape of it, that it's curling back towards the origin and stuff. Okay, now let's look at part D. Find the value of theta from, this is important, it gives a different interval from 0 to pi over 2. So, okay, that corresponds to the point on the curve in the first quadrant. They even emphasize that that's in the first quadrant with greatest distance from the origin. So we want to find the maximum distance from 0 to pi over 2. So we're not looking past pi over 2. Where's pi over 2? Obviously, it's straight up. There's pi over 2. We're not considering any of these spaces because, obviously it gets very far away out here. That's the furthest in the whole space. But we're not talking about any of these regions that are covered here. We're only covering from 0 to pi over 2 in angle. So I think it's pretty clear that, that spot is the furthest. See how it gets further out, and then at some point around here, I don't know, maybe right there or something, it starts to finally curl back in. So it's getting further and further and further, and then it starts getting closer. And we only go until pi over 2, so that's it, even though it does continue seemingly to get closer. So it's going to be somewhere around here, which again I'm predicting is pi over 3. I haven't really plugged it in to see, but I got to imagine that that's the maximum. How do we check this for sure? Well, maximums, greatest distance, so in other words, maximum r, maximums happen when r prime goes from positive to negative. So let's look at dr d theta and see when does that go from positive to negative. Dr d theta is 1 plus 2 cosine of 2 theta. And we know obviously that starts at 1, so we can investigate the endpoints all we want if we plug in 0 to the original function. So actually let's do that as well. Let's find r of 0. Oh, we already talked about this. R of 0 is 0, and r of pi is just pi. So now we're looking for critical points because that's where we can also have maximums and minimums. So critical point is where this equals 0. In other words, cosine of 2 theta equals negative 1/2, which means that 2 theta equals the cosine inverse of negative 1/2, which a calculator will tell you. What will a calculator tell you? A calculator will tell you that this is 120 degrees, or if you're in radians, it'll tell you that this is 2 pi over 3. Thing is, it's technically 2 pi over 3 plus 2 pi n, and because of the cosine inverse rule, negative 2 pi over 3 plus 2 pi n. Why is this important? Because we have an interval that we're given. So when we try to solve for theta, if I divided 2 on both sides, I would say theta equals pi over 3 plus pi n, and also theta equals negative pi over 3 plus pi n. So I have to consider these possible angles. So of course pi over 3 is the one right on the money. And then there would be 4 pi over 3, ... These are all excluded because they pass the interval from 0 to pi over 2. That's a very important interval. Anything further than 4 pi over 3, and even on the other side, anything like less than that, so like negative 2 pi over 3, that's too far back. So this is the sweet spot. And then for here, we start off with negative pi over 3. That's obviously not going to cut it. If we add pi over 3, we end up with 2 pi over 3. That's not going to cut it either. That's past pi over 2. That is too far. So none of these are working because the region that we're working with is in between here. So like, of course, negative 4 pi over 3 and so on. That's not going to work. So our only angle is pi over 3. Now, does it ask for the radius? Does it ask for the distance? No, it does not ask for the distance. It asks for the value of theta that corresponds to the point. And so we have found it. Theta equals pi on 3. I know I squished it like right next to this other boxed answer, but that's okay. I'll just label it part D, and I'll label this part B. All right, pretty straightforward, guys. I mean, this was a involved problem, so certainly needed some calculator work. But as you can see, Desmos is a tool that we're able to use at the very end of our process. Once we've already used the concepts like understanding how to find the x-coordinate in terms of theta, and then working this around to try to solve for the angle. As well, setting up the integral is a large part of your credit. You're going to get 1 point for that, and then you're going to get 1 point for the final answer. So half of it is setting it up properly. You would not have needed to do any of this unless you were solving it by hand, which it doesn't seem like this was intended to do by hand. Maybe on one of my tests, so you should be lucky that I don't give you tests and that you take the AP test instead, because the AP test is easy compared to my tests. That's enough blab, and if it felt like a threat, I'm sorry. I didn't mean to threaten you. I just want you to know that I have pretty high standards for my Calc students, and you all are brilliant and capable, so that's why I have the high standards. I wouldn't have them if I didn't think you could live up to them. Enough of the blab, even enough of the little lighthearted motivation at the end. That's enough out of me. I'll see you guys next time in the void.